photo files that we have are infrared if we don't have any infrared LEDs. So what we're going to do is that you're going to have to take your photoresistor and point it in one direction, right? And then this will go into your breadboard, and you're going to have to mount your LED like this. Makes sense. It's still going to pick up ambient light, but we can do enough with this to figure it out. Then we got a circuit control into our LED. And of course, we're going to do this with a potentiometer, right? And what else? We got a resistor here. And then we got a LED. Four bias, right? Way okay so far. And then what are we going to do on the other side? Yeah, we're going to put our photoresistor over here. Is there a resistor? No, we got to put a resistor in series with it because we got to measure, right? And then we'll put our photoresistor right here. And then we'll come back over here to our power source. Goes over to the same power source, right? And then what are we going to be able to do here? We can measure right here. I don't know what size it is. What size is this resistor there? All right, right, the LED is one thing not about an LED is that this is the problem we had when they started doing fluorescent bulbs. Fluorescent bulbs, you couldn't put them on a variable light. So it was very, very complicated to do that. And they did put out some, but they were very, very expensive. So what's nice about LEDs is that we can control their brightness by changing the voltage on the bright. You understand that? So this is why fluorescent bulbs are starting to go out as far as lighting. Incandescents, by the way, are going to be outlawed in your lifetime, right? And why is that? Because they create light by heat. Heat requires a lot of current. Right? Fluorescent bulbs create light by sending electrons to the gas. So they have extremely high resistance. And they don't use current. So this is why we started adopting from incandescent over to fluorescent. LEDs, they produce light by combining, right? They produce they require very little current, and they can put out quite a bit of light. But what's nice about an LED is we can control the light as well with applying different voltage levels. So I just went out and bought some, and they give me the equivalent of 40-watt bulb at 4 watts worth of power. But you get the equivalent of light out of you would get if you went out and bought a 40-watt bulb, but you're only 4 watts of power. Yeah, you don't have much combination with fluorescent bulbs. Fluorescent bulbs, you have to exceed a certain amount of current to cause them to fluoresce. You have to automatically drop it down to cause it to work. So what happens if you let them start fluorescing and you don't control the voltage, it'll just keep the resistance of the bulb keeps going down and it would burn everything up. So we have something called a ballast. Y'all know what the ballast is. So the ballast allows it to start maintains the volt. It actually acts like a resistor, but it passes through to start, and then acts like basically a variable resistor when we try to pull more current, which is pretty neat. So the ballast is not cheap either, so we don't have ballasts. So they do all the rectification and everything inside the bulb, which is pretty neat. And we can do what? We can dim it. So this is probably the route that everything's going to start going, except in here. By the way, you can buy fluorescent tubes now. They're not fluorescent tubes, but they're compatible tubes with their LEDs. They're about LEDs, and you plug them into this. And so yeah, there was one companies went work with an. So they basically had to take out the ballast, flip off the ballast, and plug in bulbs, which is pretty neat. So if I understand that, y'all okay on that, you'll see how this is going to work. So we're going to measure current indirectly, right? You understand that? And then we're going to the lab calls for a certain amount of current to do. So this is the amount of current we put in, right? You understand? Or this is what we get out, right? You understand that? So what should we expect across? So as the light of the LED increases, what should we expect the resistance of the photoresistor? So the voltage you drop across this is going to go down, right? You understand? And then the voltage you drop across this resistor is going to go up. Current is going to be going up too, right? You understand? So these currents in the photoresistor and the current in the light bulb should vary in what? The same direction. That makes sense. You okay on that? You understand how this is going to work? Y'all got any questions? How many times I ask? No. The resistance drops. If the resistance drops, the current's going to go up, right? You understand? So what's going to happen if the resistance drops right here, then RT is going to do what? This is a fixed resistor. So if this guy right here drops, then RT has got to be doing what? Going down. If RT goes down, what's going to happen to IT? It's going to go up, which is going to cause this resistor to drop more voltage, right? You understand? And this guy's a lower resistance, and the sum of the voltage drops still have to equal to the applied voltage. So as the current flow through this goes up, the current flow through this is going to go up. Should go up by the same percentage, right? You understand that? Are we okay? But you're going to have to point this LED what? At it. You're going to have to basically touch. So this is the schematic. Physically, your LED is going to be over here, right? Into your circuit board. And then you're going to take that photoresistor and you're going to basically, they're going to touch each other in the center. So that's the way you're going to mount it. Now you're going to get current flow to start off with because the photoresistor is picking up the ambient light right in here already. It's not going to pick it up as fast because we're pointing the sensor away from the light up here. So we can control it a little better. We could wrap it in black tape, but there's no reason. You'll see how this thing works this way right here, right? Are we okay? Okay, so what's the next one? What's the next one? Photovoltaic cell, right? So what we're going to do here is we're going to go to the incandescent light. Hopefully I can find some. If not, we'll have to use the LED. This is a symbol for an incandescent light bulb, right? This is a symbol for a gas light bulb, which is a neon or fluorescent, right? Okay. So this is an incandescent light bulb. And what are we going to do? The same, basically the same circuit, right? We're going to have, we got a resistor right here, and then we got our pod. Same circuit. Yes. You'll see this big thing right here. Okay, so y'all did skip over that, right? So this is a photovoltaic cell. Okay, this is the light bulb. That's the one. This is the symbol that the electronic workbench uses, which is not the standard symbol. So I see they've got the little circle drawn upside down. Can y'all see it? The little loop right there. They got it drawn pointing in instead of pointing out, but that's okay. So we're going to use a 100 ohm resistor. Basically, we're using the 100 ohm resistor to do what? Yeah, that would do that as long as if it was a 12 volt bulb, if we adjusted the trigger to 12 volts, then we wouldn't need a pod, we wouldn't need a resistor or anything, right? You understand? I don't know what it tells you to set this at. What does it tell you to set it at? 12 volts. I don't know what the little light bulb's rated at, but so it could be in their protection. So if we set this to 0, but the main purpose of that is so we can measure current without using an ammeter, right? Right. 10 milliamps per volt. You don't even have to do your calculations. So if it measures 1 volt, that means it's what? 10 milliamps, right? So that's real nice about a 1K resistor or a 100 ohm resistor is that you can do your math without doing your math, right? You can do your math in. So it's 10 millivolts per volt. So if I measure 3 volts, 3.5 volts across that resistor, it would be what? 3.5 mil. It'd be 30.5 or 35 milliamps. Are you okay? So we're getting up to 60 milliamps on there. So that's why we got a 12 volt supply. 60 milliamps means this guy right here has to drop 6 volts, right? So anything above 6 volts would be okay, but are we okay? So it's going to say measured IC. So that's and we're using a 10K over here for the same reason. First of all, this is a voltage source. And if we measured with our meter got 10 mega ohms worth of resistance, it would vary, but it wouldn't give us what it would give, what we would see under a load, right? Understand? So what that means is a solar cell, it has internal resistance, so the amount of current you get out is going to be at a certain load, right? You understand? That makes sense. So here we a photovoltaic cell. We're going to adjust this. So what should we expect the voltage to do as we adjust this? This is a solar cell. But technically, we call them solar cells. I'm sorry. Commercially, we call them solar cells. Technically, they're called photovoltaic cells, right? You understand? So what should we expect to happen when the light on this thing goes up? Yeah, the voltage on the output will go up, right? You understand that? And then we're calculating the current here. About this resistor right there, right? So we can measure the volt. Okay. So this will be 100 milliamps. This is 10K. This will be 100 milliamps per volt, right? No, I'm sorry. It'd be 100 micrograms per volt. Went the wrong way, Rich. Okay. So I know what y'all going to anticipate there, right? Everybody okay? Okay. I think it's only